This is Rosen, Discrete Mathematics and its Applications, section 5.3 on recurrence relations and structural induction. Here we discuss a result related to the Fibonacci numbers. And you might recall that the Fibonacci numbers are defined as a recurrence relation as follows. I have a basis case of Fibonacci 0 is equal to 0 and Fibonacci 1 is equal to 1. And then my recurrence relation of degree 2 is Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n to the Fibonacci n minus 2, where n is greater than or equal to 2, so that I can take advantage of the basis. And if we find some of the higher Fibonacci's, we'll just use the recurrence relation and run it on out. Fibonacci 2 is Fibonacci 1 plus Fibonacci 0. 1 plus 0 is 1. Fibonacci 3 is Fibonacci 2 plus Fibonacci 1, and 1 plus 1 is 2. Fibonacci 4 is Fibonacci 3 plus Fibonacci 2, 2 plus 1 is 3. And Fibonacci 5 is Fibonacci 4 plus Fibonacci 3, and 3 plus 2 is 5. And in Chapter 8, we'll delve into this more. We'll look at the historical motivation that Fibonacci used to develop this recursion relationship, this recurrence relation. And it's based upon his theorizing of how the population of rabbits would grow on an isolated island. All right, so next we're going to prove a result related to the Fibonacci numbers. We want to show that whenever n is greater than 3, Fibonacci n is greater than alpha to the n minus 2, where alpha is this value right there, and I'll tell you that value is closely related to the golden ratio. And it comes out of the recurrence relation for the Fibonacci numbers. 1 plus the square root of 5 over 2. So Pn is our statement. Fibonacci n is greater than alpha to the n minus 2, where alpha is defined above. We're going to use strong induction to show that Pn is true whenever n is greater than or equal to 3. So we have two basis cases. We have P3, and P3 states that alpha to the first power is less than 2. And we can see that because 1 plus square root of 5 is less than 4. And that number divided by 2 will be less than 2. And 2 is Fibonacci 3, so Fibonacci 3 is greater than alpha to the 1. P4 holds since a squared is 3, alpha squared is 3 plus square root of 5 divided by 2. Well, 3 plus square root of 5 is less than 6, so that divided by 3 is less than 3, which is Fibonacci 4, and the basis cases for P3 and P4 are proven. All right, let's set up our inductive hypothesis. Pj holds, that is, Fibonacci j is greater than alpha to the j minus 2 for all integers between 3 and k is greater than 4. We want to show that pk plus 1 holds, that is, that Fibonacci k plus 1 is greater than alpha to the k plus 1. All right, pause to note that alpha obeys this relationship here. Alpha squared is equal to alpha plus 1, and I'll leave it to the reader to square alpha plus 1 and show that it is 1 greater than alpha. And that comes out of the solution here, the solution to this polynomial here, which we will learn later is the characteristic equation for the Fibonacci recurrence relation. In any case, alpha squared is equal to alpha plus 1 is very easy to show, and I'll leave to the reader to do that. Now let's prove pk plus 1 by tackling alpha to the k minus 1 first, and we'll show that it's less than Fibonacci k plus 1. All right, so alpha to the k minus 1, we're going to split that up into alpha squared times alpha to the k minus 3, but as I mentioned, alpha squared is equal to alpha plus 1, so I substitute to get alpha plus 1 times alpha to the k minus 3. And now I distribute. I get alpha times alpha to the k minus 3 plus 1 times alpha to the k minus 3. That's alpha to the k minus 2 and alpha plus alpha to the k minus 3. Now, we will be able to say something about these because of the strong inductive hypothesis. Since k is greater than or equal to 4, both of these are captured in our inductive hypothesis, and Fibonacci k plus 1 is going to be greater than alpha to the k minus 3. Fibonacci k is going to be greater than alpha to the k minus 2. That's all by the inductive hypothesis. And then it follows that f of k minus 1 is equal to f of k, Fibonacci k plus 1 is equal to Fibonacci k plus Fibonacci k minus 1 by definition. And these are greater than alpha to the k minus 2 and alpha to the k minus 3 respectively, but their sum equals alpha to the k minus 1. So Fibonacci k plus 1 is strictly greater than alpha to the k minus 1. And thus pk plus 1 is true. We will use this result in an important proof that follows. So we'll stop this video here.